Good afternoon, everyone. Today I'm going to give a presentation with the topic of integration of real-time three-dimensional capture reconstruction and light field display. And my presentation will be divided into 5 parts as it lists. Okay.
Here you go.
Okay. And starting with the first one, the basic principles of the true 3D concept. As you could see from the picture, the true 3D will provide you with the things that you could see the correct perspectives from the at the correct position, just like you see something through a transparent window, and even you could neglect the window. And actually, you could see things, experience the three-dimensional feelings because the images will provide you with 3D cues. For the two-dimensional images, the monocular cues works. It includes the linear perspective, occlusion, or something else that makes you feel that you see things three-dimensional, while in fact it's two-dimensional. And for the binocular cues, there are usually a pair of images with slightly difference that you could feel the accommodation, convergence, or motion parallax, or binocular parallax that you might just see from my previous presenter. And so, because the similarity to our brain that see things in a natural way, the binocular cues is more similar to the way that we feel the real world. So, in our system, we focus on the binocular cues. And here to the end-to-end true 3D system concept. The end-to-end is pretty self-explanatory. We got an input end that captures the data, and we got an output end that displays it, and we got some transmission module or reconstruct module that connects these two ends. The realizations from the reference papers are listed here, but not limited to them. The realization is 3D TV or free viewpoint TV that consisting of the camera array as the input and connected by the transmission module to the output, usually in the form of a light field display. And there is a typical system. It's from MOSIX and Piffre's three-dimensional TV. And focus on the input end, there are light field data acquisition at the input end, and they are subclassified into the camera array acquisition, the micro lens acquisition. And some special about the moving from the random array, it's like the many tourists, they took pictures of the same architecture, and you could collect the data, and no matter, and neglect the differences of the capture devices they use, they could still use the light field data from their data. So we count it as some special light field data acquisition method. And the process, here we focus on the reconstruction process. The light field construction could be performed using the light field data, but it usually cannot get some physical information from it. So the surface reconstruction came in. There are 2 kinds of it, and we focus on the multi-view surface construction to get the physical information, and then generate the light field data out of it to feed the data to the output end, which will be the light field display as it shows. And there are also general classification about it. The binocular stereoscopic display, as my previous the previous presenter has shows to us. It wear glasses and you see two slightly different images with 2 eyes, and there are auto stereoscopic display that you either render things at a rotating form, the 3-dimensional medium, or you're using a projector array to render 3D dimension at the flat screen. And what we try to achieve is that at the input end, there is camera array-based acquisition, and we reconstruct using the data captured to generate the light field data and to feed it to the projector array and display it. And so let's see the system. Two key principles of the system is the reconstruction and display. Start with the construction. The traditional reconstruction way is to extract the feature and matching the features and perform the reconstruction. It fails when there is an uneven distribution of the feature, or the feature is not enough. So we apply the state-of-the-art, the global optimization, which is based on the expression below. It converts the match process into the energy minimization. So we could use a preset z value for each pixel and calculate their errors. So there is a cost of volume constructed, and to minimize the cost of volume, and we can get the fittest z value for each pixel, and we got the depth information. And this is the display principle. It's actually a remap of the light field. Suppose we have correctly got the reconstructed surface, and we extract each perspective of it from the virtual camera, and each projector will project it through the VDOF screen. VDOF stands for the vertical diffusion only. As the right image shows, it will diffuse the light mainly at vertically and rarely at the horizontally. So the viewers so we just put several projectors into the same place, and the VDOF screen will remap the light for the viewers, and the viewers could see and only could see the corresponding images that we let them know, and they will feel the three-dimensional feelings. And this is the hardware components. It consists of the VDOF screen, control PC, a display array, and sparse acquisition array. It shows six cameras. And here's how we get it. There are three software modules, and the first one is the construction module. It's here we use sparse camera array or SRC because we want to acquire the actual dimension information, and we want to increase the reconstruction accuracy. So we don't use only one moving from the camera, and we don't use stereo. And this is an acquisition module. Suppose we use some camera lens with low quality. There is distortion. You could see from the left images the dark part of the four corners is because it has a large distortion, and we calibrate it and undistort it. And we also need some denoising or some other pre-processing steps. And we calibrate and get the intrinsic and extrinsic matrix of it, and then we could perform it using the parameters that we have got from the previous calibration step. Below here we use the non-parametric local transforms instead of the common SSD or other ZSSD cost to compare their difference. It compares the difference trend instead of the difference itself, so it proves to be more efficient to pick the same point at the target camera and the reference camera. And here we add the semi-global steps into the reconstruction module. Its cost aggregation is performed in a sub-pixel interpolation way, because we not only compare the pixels nearby, but the pixels we interpolate into them. So the index of the pixel we compare is not an integral like the 1 to, but 1.5 to 2.5, and this could be achieved. This could be achieved easily if we're using some software. And here is the core of it. So the disparity calculation is realized by decoupling the data term and the regularization term. The data term is lambda by the CR, and the regularization term is R, and the Q is the auxiliary function added. So the whole expression could be could not be a non-convex problem anymore, and could be solved by some iterative algorithms, and or by some dual problems. So, and this is what we try to solve it. Besides realize the algorithm that's based on the existing theorem, we use the SRC-based acquisition with preset parameters, not use the parameters that updated when we camera it, as the reference said. And we introduced the semi-global matching in the global optimization to get a finer result. And also we use the dynamic threshold to get the more accuracy in our results. Because in the original semi-global matching, the threshold is static, and we modify it so the result is more fine, as we can see from the picture. The edge is more obvious. And here is the last part. As we have got our depth value, we still need to mesh it and do some other post-processing steps. So MeshLab is what we use. It provides many APIs, so we can use them to do this. And after we got the meshing and textured and clean modules, we could use the virtual cameras to get the many perspectives, as many perspectives as we needed it. So the light field data could be get. And here is the display module. As we use the projector array, so projectors at the positioned differently should project the images at the same place. It will, if you use it, you will see that if projector is not vertical to the plane that it projected, it will be irregular rectangulation, not the regular rectangulation. So the alignment is needed, and we use the homographic transform, and there is a coordinate unification steps. That's this tilted images is captured by the camera, so the coordinates is camera determined, and the standard chessboard images is under the image coordinates, and there are also the screen. We need to print to the screen, so the screen has to be projected into the camera coordinate system, and we unify all this system together, and we could do the alignment. And this is a render module. From the, as has shown before, the VDOF has its mathematical module, and according to it, we could remap the pictures. But from the side view, because we render actually a flat image and let the observers saw it as a 3-dimensional, so there is a mismatch between these two. So offset factor should be added. You could see from the two curves, if there is no offset factor, it will be some distortion vertically, and after it would be seems normal. And what we tried is that to accelerate this, we use HLSL, which is a high-level shading language, to accelerate the render process. Also, we use the lookup table to accelerate the alignment process. And this is our experimental results. We first make a simple comparison. The alpha factor is we increase the alpha factor in the in the expression we have we have previously mentioned, and you could see it got less smooth because the regularization is the weighting factor of the regularization is small, so the data item dominates, and the smooth effect is weakened. And the same story happens when we decrease the lambda, which is the data item's weighting factor. And this is a comparison between the common method to reconstruct it and the way we use it. The NPLT plus SPIE plus DT perform the best quality reconstruction. And here we got some images from the standard database. We can see that these quality are almost the same even using our optimized. One thing noticing is that we do not know the extrinsic matrix of these images, so we use other software to estimate the extrinsic matrix. This might be affect the efficiency of our algorithm, and this might be some test images from Microsoft's DirectDX. I'm not sure it, so I just put his links here. Not sure what the image is from. And this we could see some details improvement if using our algorithm. And here is the demonstration of our reconstructive model displayed in our system. You could see that the dynamic. We just pick full perspective views of the rendered and the displayed object. And here is the two demonstrations. This is the pre-rendered curves, and it shows that the motion parallax. You could see this part. It will change its area as we move our viewpoint. And this is a dynamic. We capture it real from our input end, and this is the output end. And this conclusion is that we emphasize upon the multi-view light field display and using maybe SAC, maybe it's a typo, SAC-based acquisition. Our end-to-end system contains an auto-stereoscopic three-dimensional system in the packed form at the output end, and the acquisition system featuring sparse camera array at the input end, offering light field data out of the real-time construction for the output end. And the future work is that we might customize the hardware to accelerate the whole process furtherly, and the form of the output end varies. Maybe we could use the data to do some 3D printing or some others, not limited to the display. And this is an acknowledgement from the one that not listed as authors. And thank you.